Welcome to Policy Talks. I am Etimov Young. South Africa has a strong space heritage with deep roots in astronomy and appears to be the leader in astronomy in Africa. It boasts of several observatories, some of which are used to support current space missions of international clients, including the UAE and the U.S. More recently, South Africa won the hosting rights for a large part of the Square Kilometer Array Observatory, which will be the largest and most powerful radio telescope in the world when completed. Last week, South Africa hosted the third conference of the African Astronomical Society. In 2024, South Africa will host the General Assembly of the International Astronomical Union, the first time the meeting will be held in Africa since the founding of the organization in 1919. To strengthen its local expertise, facilities, and capabilities, the South African government enacted the Astronomy Geographic Advantage Act in 2007. What real advantage has the Act contributed to the South African economy and technological capability? My guest is Dr. Adrian Tiplady, Deputy Director for Strategy and Partnerships at the South African Radio Astronomy Observatory. Dr. Tiplady, joining us from Johannesburg, welcome to Policy Talks.
Thank you very much for having me. It's great to be here.
Thanks for coming. Let's start with the just concluded conference of the African Astronomical Society, which was held just last week. What were the major takeaways from the conference?
I think one of the important things about, even being able to have a conference with such a wide diversity of participants suggests to me that astronomy and particularly my field, radio astronomy, is an area of activity that is really growing from strength to strength on the African continent. We've been hugely excited from the SARAO perspective in terms of the opportunities of investment in research infrastructure and research and investment in astronomy and space science across the African continent, and the potential benefits that may arise. There's a huge number of areas in which astronomy and the development of skills in astronomy can really deliver socioeconomic benefit and socioeconomic impact in a variety of different countries. So I think that for me is the biggest takeaway, is really just the diversity and the strengthening of the astronomy community across the African continent.
Okay, let's look at like you mentioned the growth in astronomy in Africa. Let's take a brief look at the numbers. So like how many professional astronomers do we have in Africa? Any idea?
So that's a very good question that I probably don't have the numbers off the top of my head. However, that being said, I'm a bit more familiar with the numbers in South Africa. Where if we just look at the radio astronomy community, we've grown from perhaps up to about 5 practicing professional radio astronomers in South Africa when we first started the SKA program, something like 20 years ago. And that's growing to quite a diverse and sustainable community of the order of 200 or so. And that's been developed through quite a strategic intervention, which was implemented through the South African Radio Astronomy Observatory, but with funding from the Department of Science and Innovation, where we developed a pipelined bursary program that provides support today from school level all the way through to postdoctoral fellowships and research chairs within the South African university environment. And we've given approximately 1,500 or so grants and bursaries to various students, not only from South Africa, but also from our African partner countries within the SKA program. And we've seen a significant strengthening, I believe something of the order of at least 100 to 200 grants and bursaries have been given to students from various African countries. And what has been exciting has been to see those students graduate, go on to their PhDs, and return back to their countries to establish, right now, quite vibrant astronomy programs in the various countries. Like I'm thinking of, for example, Ghana, Namibia, Botswana, for just to name a few, that have gone ahead and established sustainable astronomy programs within their universities. And some of them are, in fact, pursuing the establishment of radio astronomy infrastructure. So, for example, and we may get onto this later, but the Ghana Radio Astronomy Observatory and establishing that has really seen this growth of research infrastructure platforms across the African continent that can support the establishment of astronomy.
Yeah, that's cool. And one of the facilities or places or the tools you use for your work is the observatories. Can you give us a sense of how many observatories in Africa and kind of the spread also?
Sure. So there's and obviously there's been a growth in radio astronomy observatories more recently, particularly following the investments by the South African government. But at this time, we've obviously got a history and a legacy of radio astronomy observatories in South Africa, particularly. So we've got the Hartbeespoort Radio Astronomy Observatory, as well as a number of radio telescopes located in the Karoo region of South Africa. So that includes the Meerkat and a number of other international projects that we host. But more broad, we've got the Ghana Radio Astronomy Observatory, located just outside Accra in Kuntunzi. And that's in fact been a program or been a project that has been implemented pursuant to what we refer to as the African VLBI network. And that is a program amongst a number of African partner countries, including South Africa, Namibia, Botswana, Mozambique, Madagascar, Mauritius, Kenya, and Ghana, to drive the establishment of radio astronomy research infrastructure platforms across the African continent. We've also got radio telescopes that have been used in Nigeria previously. We have the HES telescope, which is, and when I say we, collectively, I'm not saying they're SARAO operated, but there's the HES telescope, which has historically been used in Namibia. And there are programs and discussions afoot to look at the establishment of new radio astronomy infrastructure, both in Namibia and Botswana, who have just recently approved an astronomy and space science policy that identifies astronomy as an area in which to attract science investment into science and research, and also as an area in which there is a potential advantage for investment by the relevant governments.
Yeah, and like you mentioned earlier, many people from other African countries have come to South Africa for maybe education or research, and then they go back to their countries. Can you give us a sense of universities when it comes to teaching or research? In terms of numbers or an idea, averagely, how many universities are offering academic programs in astronomy? What research is going on in different parts of Africa?
Yeah, absolutely. So again, starting from South Africa, there's I'd say off the top of my head at least 1, 2, 3, 4, perhaps about 5 or 6 universities that are delivering courses in astronomy, radio astronomy, but also what is important is in the engineering disciplines and technical disciplines required to support the development of astronomical facilities. So in fact, it's not just the science side, but also within the engineering departments within the universities that there's support. I can note, for example, the Botswana Institute for Botswana International University for Science and Technology that is establishing a very significant astronomy research program with a chair of astronomy, and they are looking at deploying and investing in radio astronomy infrastructure in partnership with this other partners. We have historically courses in Mauritius, which also has a history, quite a long history in low frequency radio astronomy, and we've got a number of partnerships and with various researchers and students that have come out of Mauritius. So in terms of the exact numbers, and I'm a bit worried that I might leave out a few, but I've just kind of pointed out a few notable exceptions in that there's been significant investments taking place by the respective countries. There's also, we have a very good relationships with Ghana, in particular the GSSTI, Ghana Space Science and Technology Institute, as well as universities in Kenya. So I think there is at various degrees, that some of these courses only go up to master's level, some don't necessarily go up to PhD level at that point in time, at this point in time. But I think that's just a few examples of where astronomy is really starting to take off within the university curricula.
Let's talk a bit about the upcoming IAU General Assembly, which is actually one of the major discussions that came up during the conference last week. First of all, why did it take over 100 years before the General Assembly gets to be hosted in Africa?
That's a very good question, and I wish I could give a coherent answer to that. I think the same question could have been asked about the Soccer World Cup, and almost this is like the World Cup of Science or the World Cup of Astronomy coming to Africa for the first time. And I think it's really important. It's a really important statement in recognizing the significant growth and strengthening of the astronomy community in Africa. Historically, a large bulk of investments in research infrastructure, in astronomical facilities, has taken place within the Northern Hemisphere. There's a significantly less investment that has taken place in the Southern Hemisphere in astronomy. And I guess also traditionally, the researchers and the research communities would be located near the research infrastructure platforms historically. But with the growth of internet and connectivity and the ability for researchers not to have to travel to telescopes, but actually to access the telescopes remotely and access the data that is generated remotely, it has meant that there's been a wider distribution of the community, I think. But coupled with that has been the increasing investment in radio astronomy research infrastructure in the Southern Hemisphere, and particularly within Africa, recognized by investments in both the MeerKAT and the future SKA program in the African continent. I think the hosting of the General Assembly in Cape Town in South Africa is recognizing that and recognizing the growth and diversity of the astronomy community in Africa. I think that's really important. As to why it hasn't happened in the past, I can best. I'm not. I guess I'm not the soothsayer. I don't necessarily haven't been part of the decision-making processes historically as to the location of the IAU General Assembly, but I think it coming to Africa is probably a real recognition of the investments and the growth of the community.
So the formal announcement was made in 2018, even though there have been preparations for the conference, I believe, before 2018. So now it's coming up just next year. Can you give us a sense of the level of preparation for the conference? I know there's been a lot of work that has gone into the preparations.
Absolutely, and preparing for a major event like this can take years. Securing venues, for example, would need to take place at least 2 or 3 years in advance to identify just a venue that can accommodate the size and the number of visitors that will visit South Africa in the area. So producing and developing scientific programs, etc. I think just the the amount of resources required in order to ensure a smooth running event is substantial, and it can take many years. And we have a local steering committee in South Africa, and there are some people that have been working on this full time. So it is a substantial amount of effort that's required to ensure a smooth conference and a smooth General Assembly.
And it appears the African astronomy community is really excited about the opportunity to host the General Assembly. The non-African, the expected visitors, is there a similar excitement from their end also?
I think absolutely. I think apart from for many of them it will be their first visit to Africa. But also, given the investments that have been made over the past 2 decades in astronomy, I think it's also extremely exciting, and there's been a number of international partnerships and collaborations that have formed with the international community. And it's an opportunity for those international collaborators to actually meet with the local African scientists and astronomers face to face, especially over COVID. I think that's been quite difficult. So I think it's an opportunity to really form strong partnerships and collaborators, and also for the international community to get a sense of what is happening in Africa. There's been a lot of talk about, and I'll speak from my own personal experience, a lot of talk about the investments the South African government has made in MEERKAT, the SKA program. And I think there's a huge amount of interest to understand, given that this has been a South African designed, South African funded, South African designed facility, I think there's a lot of inquisitiveness, right, around hosting of globally important research infrastructure in Africa. And for many, I think it's their first experience engaging with those kinds of projects, those scientists and engineers in Africa. So I think there's a huge amount of excitement from both sides.
Are there positive expectations, or a kind of let's just go and see what's happening? There are really some real positive expectations from the conference. Certainly from the conference, I think there's a wide range of expectations, or positive expectations, as you put it. Obviously, forming and establishing collaborations and partnerships with the international science community, but also investment in research infrastructure in the African continent has provided a vehicle for mission-driven innovation, that provided an enabling environment for development of innovative and new technologies. And again, speaking from personal experience and from my own institution, the South African Radio Astronomy Observatory, that it provides an opportunity to showcase skills, technologies that have been developed for existing research infrastructure platforms to the international community, and provides an opportunity where we can kind of showcase ourselves as a potential partner to the global astronomy community in providing both science and technology solutions. And that's really important, right? That's starting to ensure sustainability in the investments, sustainability in the people and the skills that have been developed, and providing potential future impacts, socioeconomic impacts, not just looking at the skills development, but actual
participation in international projects, delivering of technologies and scientific skills into those international projects. So I think that there's a huge amount of potential spin-off benefits and socioeconomic benefits that may arise, and the General Assembly is not the only opportunity, but is a key opportunity to be able to interact and engage with the global community.
Let's talk a bit about the SKA. What's that's the Square Kilometer Array project? What's it really about?
So, I mean, the idea of the SKA began in almost the early 1990s, looking at what were some of the most fundamental questions being posed by the astronomy community. And in order to answer many of those questions, it was conceptualized that we needed to build the biggest, most impressive radio astronomy facility in the world. Something that was between 50 and 100 times more powerful, more sensitive than anything that had ever been built in history. The problem with that, almost 2 orders of magnitude improvement in capability was that much of the technology didn't exist at the time. And so it took a number of decades to start understanding and developing the technologies that will be required in order to process the huge amounts of data that will be generated. So ultimately, the design and the thinking, the concept of the SKA evolved. Originally, it was called the SKA, Square Kilometer Array, because of the idea that we would need a square kilometer worth of collecting area. The bigger, the better. The bigger a radio telescope is, the more sensitive it is, and the weaker the signals it can detect. And those weak signals are signals that have been traveling through the universe for billions of years. And so they are old historic signals, which provide us a glimpse of the universe in its past during its creation and evolution. Right. So many of the signals we would detect with the SKA originate back, 12, 13 billion years in the history of the universe. And so enable us to kind of view and detect the formation of the very first stars and galaxies and the evolution of the universe up until today. So today the SKA is, we went through quite an extensive site selection process. But ultimately today, the SKA telescope is going to be constructed both in Western Australia as well as on the African continent, initially starting in South Africa and then growing out to a number of African partner countries. So in Africa, at its greatest extent, it could be up to about 2,500 radio telescopes or dishes, distributed over an area of something like 3, even 4, 5,000 kilometers in extent, which would include countries of South Africa, Namibia, Botswana, Mozambique, Madagascar, Mauritius, Zambia, Kenya, and even Ghana. That is being constructed today, and we actually have issued the very first contracts for construction, where we'll deploy the first phase of the SKA, which is approximately 10% of the size of the full extent of the SKA, so up to about 197 dishes located in South Africa, in the Karoo region of South Africa. In Western Australia, we won't be deploying dishes, we'll be deploying low frequency aperture arrays, so really targeting the lower part of the radio frequency spectrum. And those signals that we'll be looking for are really the very earliest hydrogen signals that were generated and that were emitted at the beginnings of the universe, the stars and galaxies that turned on.
You mentioned that there are 8 partner African countries. What were the criteria for selecting these 8 out of the 55 countries in Africa?
So I mentioned earlier, the bigger the better. The bigger a radio telescope is, the more sensitive it becomes. The problem is when you build a very big telescope, it becomes very difficult to point it. Right? It's a very large dish and becomes very difficult. In fact, one of the biggest radio telescopes in the world is located in China called FAST. It's 500 meters across in diameter, but you can't move a dish like that, and so it points directly up ahead, above it, and it's able to point a little bit, but it's not quite as much as a fully steerable dish. And so what we do as radio astronomers is we actually break up one giant dish into lots of smaller dishes, which is why I say that the SKA will be up to about 2,500, 3,000 dishes, which will all be connected into one big giant supercomputer. Now, the other characteristic about an array of telescopes is that the further you distribute the dishes apart, the better the resolution of the images you produce. So you can imagine your TV screen, the more dots per inch that you can produce in your image. And so the configuration of the SKA is driven by scientific performance factors. It's not only how far you distribute it, but the manner in which you distribute these dishes. Now, the best kind of configuration from a scientific perspective may be a completely random distribution of dishes. I could, throw up a bunch of marbles into the sky, see where they land, and connect all of those together and create a high-performing, high scientifically performing instrument. The problem with that is you got to connect all of those together with infrastructure and connect all of the data streams together, and that becomes very, very expensive. And so we adopt a specific array configuration that will enable us to optimize both the scientific performance of the configuration, but also make it realistic in respect of the costs and the infrastructure that needs to be deployed to connect all of those dishes to a central supercomputing infrastructure. And so the the African partner countries that were identified were those that would, if we deploy the SKA configuration, we identified in which countries those dishes would land effectively and be located to maximize the scientific performance of the configuration. And so we have we have a concentration of receivers within South Africa, and then growing out until you get the remote stations located in the furthest extent, so Ghana, Kenya, Mauritius, etc.
Let's look at Ghana, the dish in Ghana. Actually, if you trace the history of the African Astronomical Society, it appears you could trace it down to the efforts of Peter Martinez of South Africa, Ayoso KK of Nigeria. So one would have expected a strong collaboration between South Africa and Nigeria when it comes to astronomy. So how come Nigeria was left out of the partnership and skipped and you brought in Ghana instead?
So again, it's really about the scientific requirements of the configuration, specifically from the SKA perspective. That being said, as one of the principal objectives of the Africa program, which is driven not only to support the SKA, but also to support the establishment of radio astronomy research infrastructure across the African continent. We've supported a number of, for example, students within our Human Capital Development Program from Nigeria and various other African countries that are not currently identified as hosting of SKA stations. So it wasn't necessarily a deliberate, there wasn't an exclusion of Nigeria, but rather a identification of what the configuration needs and the location of stations in order to maximize the scientific performance of the configuration. But that being said, I think I agree with you. Nigeria has had a history in radio astronomy, and in fact, we've supported a number of Nigerian students, and I've in fact engaged with a number of PhD and doctoral students who undertook their work at the Hartbeespook Radio Astronomy Observatory before the investments in Meerkat.
Another technical question, and that has to be with the decision to award the SKA to two countries to co-host, rather than maybe South Africa or Australia. Why did the IAU decide that South Africa and Australia should co-host the SKA?
So firstly, it wasn't a decision by the IAU. There was a separate international program, and which was later formalized into what was called the SKA organization. So the SKA organization was in fact a not-for-profit company, originally located in the United Kingdom. It was formed in around 2011, and it's subsequently been superseded by the SKA Observatory. And interestingly, the SKA Observatory is an intergovernmental treaty organization, and one of very few that have actually been established for the purposes of astronomy and radio astronomy. But the decision to split the site, so one should also recognize that there's been a legacy and a history of investments made by various countries, and particularly the telescope hosting countries, both South Africa as well as Australia. There's been a long history of investments in radio astronomy, and I think the way in which the site has been split based on technology. So we didn't necessarily say some of the dishes go into Africa and some of the dishes go into Australia. Instead, it's been based on a technology split. And that technology split, each of those technologies will be delivering against specific science cases of the SKA. And so you'll find that in the extremely remote areas of Australia, for example, the deployment of the low frequency technologies is best suited for that environment where it's extremely far away from any potential sources of radio interference. Whereas in South Africa and across the African continent, a generally higher site, so the Karoo region of South Africa, for example, it's got an altitude of above 1,000 meters. That really does support the high frequency observations that will be undertaken by the SKA. So there are scientific advantages in splitting the sites given the deployment and the suitability of the environment for the different kinds of technologies. There's also certainly an advantage in diversity of ensuring that the community is extensive and as possible and as diverse as possible. And I think also splitting the site does support the increasing that diversity, increasing the spread of the SKA project.
Oh, that's really interesting. So presently, what's the level of construction in terms of SKA now? What's on ground right now?
So right now, and it's really quite interesting. So one of the South African government strategies was, we didn't just want to be a host to the SKA and have a big radio astronomy facility in our backyard and not be actively participating in both the science and the engineering of the project. And so one of the strategies was to develop a site and develop a prototype radio astronomy facility. And what I mean by prototype radio astronomy facility is a prototype for the SKA, because historically, radio astronomy facilities and astronomical facilities have been owned, in a sense, by relevant institutions who have then brought on international partners. But the size and the scale of the SKA, we believe, was going to require a different approach. And so we decided that what we would do is we would want to make sure that South African scientists and engineers were participating in the SKA project, regardless of where it was ultimately going to be sited. And then for that reason, we started to establish a greenfield site in the middle of the Karoo region of South Africa, and started developing a prototype or precursor radio astronomy facility, which was at the time called the Karoo Array Telescope. And the Karoo Array Telescope was hugely successful. It was actually the forerunner to what is now called the Meerkat Radio Telescope. There's an interesting aside story in that, the Karoo Array Telescope, or CAT, Meerkat is in Afrikaans language, meerkat actually means more cat. And of course, meerkat is an indigenous animal, which is, you can find quite regularly within that region. So it's quite ironic. But meerkat has tested and developed technologies that would be required by the SKA. We adopted new approaches to trying to design and build radio telescopes. And what was very interesting is that the average age of the team, I remember a staff photo taking place, and the average age of the people in the staff photo was of the order of 30. A few gray-haired people, but ultimately it was about 30. And what it meant is that something like an exciting project like building the Meerkat was able to attract young scientists and engineers coming out of university who knew nothing about radio astronomy, but they knew how to build things and build new technologies. And what we did is we tried to learn everything we could learn about building radio astronomy facilities, and then set about trying to improve on that. And because we knew we needed to understand and develop better ways to build radio astronomy facilities. So ultimately what we did is we built the Meerkat Radio Telescope. So the Meerkat Radio Telescope is 64 dishes located in the same area as the SKA is to be built. It was inaugurated in 2018. And even though it was a precursor to the SKA, because the SKA was one or two orders of magnitude bigger and better than anything that had been built in history, the Meerkat itself has become one of the premier radio astronomy facilities in the world. And ultimately, when the SKA is built, the Meerkat is going to be integrated and form part of the first phase of the SKA. So, I talk about construction contracts that have been issued to construct the SKA very recently. In fact, the infrastructure contract was awarded at the end of last year. But the Meerkat itself is the first phase of the SKA and is doing much of the science and doing not just precursor. It's not just a precursor for the technology, but it's also a precursor for the science. And even in itself has delivered and made a significant scientific impact on the global community. So that's been operating, and we expect to see construction for the rest of the SKA. And even though, when I say the rest of the SKA, because Meerkat was South African funded, South African designed and developed, the upcoming contracts for construction of the SKA are the first contracts to be awarded by the International SKA Observatory. And that's due to start during the course of this year. Perhaps in the next 3 to 6 months, we'll start seeing activities on the ground. That being said, there have been a number of contracts that have been issued in the last 12 months, but it's for development of software packages. So it's a lot of work that is taking place in the various other partner countries that form the membership of the SKA observatories. So, for example, in China, which is a member, they are designing and developing the dishes that will be deployed for the SKA telescope. So the number of contracts that have been issued, which also has a interesting issue to address, and that is around this international global collaboration. The SKA project is really quite unique, where a number of partners and institutions from around the world are working on specific work packages in a very highly collaborative manner to deploy for the SKA project. So it's really exciting project. You know, the SKA project has never necessarily been owned by a single institution or a single country. It's owned by a collective. And I think it's quite unique globally in terms of international research infrastructure, that we've effectively all come together to collaborate on a single project like this.
So when we started with the kind of a little bit of history and the advancement of South Africa in astronomy. And I think to take this kind of further, in 2007, the Astronomy Geographic Advantage Act was kind of enacted, which I think became kind of activated 2009. But what really informed that law coming into operation?
So I think, you know, we can even look back to as early as 1996, where the Department of Science and Technology prepared a white paper that assessed the science and research landscape in South Africa. And it identified astronomy as an area in which, and this together with later strategies such as the research and development strategy, and collectively that body of policy documents identified astronomy as an area in which South Africa had a rich history, a legacy, but also what was called a geographic advantage. And what is meant by that is typically a research area in which South Africa has an advantage because of its inherent and unique characteristics. So, you know, one could almost say that a similar kind of argument or case could be made for paleontological research, where there are certain types of fossils that will only be found in South Africa, for example, or nowhere else. So you know, there's an advantage to investing in that because the research, you know, the investigation, much of the research happens on the ground here. So similarly with astronomy, we had environments which could host astronomical observations, either very, very dark skies, and Sutherland is a very well-known area or location in which optical telescopes have been constructed because it's got a legacy of having very dark skies, and therefore we can see the night sky with absolute clarity. And we have semi-arid, remotely populated areas, such as the Northern Cape province of South Africa, which, you know, could host radio astronomy observations. In the same way that optical, you know, light, for example, can interfere with optical observations by an optical telescope, radio transmitters can interfere with radio astronomy observations. And typically where you find people, you find a heavy use of radio telecommunication services. People want to watch television, listen to the radio, use their cell phones, etc., etc. And so what you want to do is you want to build radio telescopes in areas where there's a very low population density. And so there isn't a huge demand on the radio frequency spectrum, because that is the resource that is utilized by the radio astronomy service, the radio frequency spectrum. The less signals there are in that radio frequency spectrum, the more potential science we can get out of the radio astronomy observations. Now, it was also recognized that not only did South Africa have this inherent astronomical advantage because of the inherent scientific qualities of the sites that it has, it was also recognized that as technology drives the performance of astronomical facilities, we need to be able to find, the number of locations around the world that can maximize the potential scientific performance was decreasing. Right? You're not going to build the best radio telescope in the world in the middle of a city. And so with the ever decreasing number of potential locations and looking at the future investments in astronomical facilities, it made a very strong case for investment in astronomical infrastructure and research within South Africa. Then the decision for participation within the SKA project came about as the next great astronomical facility or radio astronomy facility. And coupled with that was a decision by the South African government to participate in the project and to submit an expression of interest and ultimately a bid proposal to host the SKA within South Africa. As part of that bid proposal was a recognition that we needed to protect those areas of astronomical advantage. Not only protect their scientific qualities, but also protect any future investments that would be made either by South Africa or international partners. And that really gave rise to the idea of unique legislation called the Astronomy Geographic Advantage Act that empowered the minister responsible for science and technology to declare areas of astronomical advantage. So almost like declaring an environmentally protected area, but an area that was protected from potential risks and interference to astronomical observations and related scientific endeavors. And that became an extremely important piece of legislation. It's unique across the world, I think, because it empowers the minister responsible for science and technology. So it's not necessarily it's not a regulation sitting with the communications regulator, for example, the communications authority, which is traditionally worldwide the custodian of the radio frequency spectrum. Typically their mandate extends to active and passive use of the radio frequency spectrum, but is not able necessarily to protect against risks such as shale gas fracking, for example, or the risk of excessive electrical magnetic interference, which wasn't necessarily a concern for radio astronomy facilities in the past, but given the sensitivity of something like MeerKAT and the SKA, is potentially a risk for radio astronomy facilities of the future. And that would be, and those kinds of sources of interference and risk lay outside the typical mandate of a communications regulator or a communications authority. And so sitting it underneath the Ministry responsible for science and technology empowered the minister to be able to protect astronomical facilities from those kinds of risks as well. And it's not just radio astronomy, it's also optical astronomy. And so the minister was able to declare regulations that would protect things such as the Southern African Large Telescope from source of optical interference. You may have heard that a large area of investment in South Africa is in the renewable energy program, and the area around the Sutherland Plateau is also an area that has very good wind resources. And when you build a wind farm, you typically want to put a aviation light on top of the wind farm as a warning to aircraft in the area because they're so tall. So various procedures and techniques had to be developed in order to ensure that those kinds of aviation lights would not cause any kind of detrimental optical interference to optical telescopes on the Sutherland Plateau.
Yeah, like you said, the act is very unique. I'm not sure I've seen any of such anywhere in the world. Perhaps there may be. And I've looked at a copy of the act. It's actually available online on the website of SARAO, I saw that there were 4 schedules. It touches on different aspects of astronomy, the issue of spectrum, the issue of land acquisition or land designation, maybe that's a better way of putting it, the issue of compensation for maybe the people who are living around there, and of course electromagnetic interference and things like that. But I mean, without going into the details of the law or the act, just an idea or an overview of the articles or the provisions of the act. Can you share a bit on that?
Sure. So, and let me just restrict it to radio astronomy, but the equivalent can be said about optical astronomy. So in the case of radio astronomy, the Act empowers the Minister to declare 3 types of areas. It's the core area, a central area, and a coordinated area. And the approach of the Act is firstly to provide varying degrees of protection. So the Minister will then promulgate regulations for each of those areas. And the reason why you have varying degrees of protection is that, well, you might have a source of interference within a coordinated area, which is typically the largest area. But a television broadcast station at the edge of a coordinated area, which is perhaps 500 kilometers away from a radio telescope, won't have a significant impact, right? So it's done very much, it creates an environment to undertake impact assessments. So every kind of risk is assessed in accordance with a prescribed process. So we have these 3 types of areas with different regulations, but underlying that is the idea of risk assessment. So each potential risk or each potential source of interference that is identified within the regulations undergoes a risk assessment. The outcomes of that risk assessment could be that the source of interference poses no risk and continue operating, or the source of interference poses a potential risk and should be amended or modified to reduce that risk. Or a third outcome could potentially be that source of interference introduces a major risk and cannot be accommodated, and that an alternative way in which that service can be delivered should be investigated. So take the case of television, for example. There are 2 ways to deliver a television service. One is through terrestrial broadcasting, and the one is via satellite. And so this also looks at another kind of strategy of implementation, is that it's not about creating a radio quiet zone, which is a term that I do not use ever, because I dislike the notion of the idea of radio quiet zone. It doesn't exist. What we're trying to do is we're trying to create an optimized environment, or an optimized radio frequency environment to support astronomical observations. So the example I gave of television, you can deploy it either via terrestrial or satellite. The satellite is already there, broadcasting satellite television. And so what we then do is we then migrate all of the receivers on the ground to receive satellite reception, satellite television, direct-to-home satellite television broadcasting, as opposed to utilizing the terrestrial television signal. And what this effectively does is it removes the source of interference out of the radio frequency spectrum and co-locates it with the existing satellite radio signal. So the regulations and the declarations are very broad. It's very much based on an impact assessment approach, and unique solutions are developed in consultation with the operators of those sources of interference. And regulations can be promulgated not just to identify and mitigate against active users of the radio frequency spectrum, but also incidental sources of interference. The inverters on a renewable energy facility. The renewable energy facilities in the area have to undergo and implement control plans to reduce their potential impact. And so it's a highly collaborative and cooperative process. Along with that, SARAO engages with essential service providers to ensure that there always is access to essential services. So, for example, aviation provides on-ground terrestrial-based radio communication services, provides safety of life services. And we need to ensure that those safety of life services are continuously accessible and delivered, but in a way that is radio astronomy friendly. And so we will engage with the sector on an ongoing basis to try to identify and understand the risks, as well as measures that can be adopted in deploying radio astronomy infrastructure. And it's been I think it's been a successful process. I think part of the difficulties in implementing very unique legislation and regulations is about creating understanding and awareness, and creating enough information that enables the public and the operators at large to interpret the regulations and understand the impact on them. And I think that is very important, and it's an area in which we've also learned as we've implemented the regulations to try to understand where is it that we need to provide information in an accessible manner, to ensure that local communities also support the notion of investment in radio astronomy research infrastructure. Because what is important ultimately is about when one invests in research infrastructure, it's not, you can have all the legislation and the regulations in the world. What is really important as well is to ensure that there's local support, that you are seen as a legitimate corporate citizen. I don't want to use corporate because it's not a commercial endeavor, but that ultimately we have what is referred to as a social license to operate. Because the best protection in the world will come as a result of ongoing investment, social investment by local communities as well, where their research infrastructure is located, and that is extremely important as well.
So it appears the Act has, three areas of, from the study I did, about 3 areas have been designated as astronomy advantage areas, and that means the Act goes into operation in those areas. I don't know whether there has been a study or maybe have an idea of the impact of this Act on the economy and the social life of the communities, the province, and even on the nation as a whole.
Yeah. So I think it goes beyond just the Act. So the Act provides for protection of the environment, but it's the Act coupled with the various policy and strategic interventions that have been approved and supported by the government. So there's a variety of studies that have been taking place. And in fact, we're busy in the middle of a study right now to look at the socioeconomic impacts of investment in astronomy and the SKA, not just within the local community, but nationally as well. And I think it's significant. At a local community level, we have specific programs that effectively lower the barriers to economic opportunity. It's historically an agricultural economy in the environment, and what we're trying to do is trying to ensure that the local community is participating within the project at an economic level, so providing, taking advantage of procurement opportunities from a skills development perspective, where local community members are being trained through we've got a variety of different interventions. We've got artisan training programs to ensure that we are able to equip the community with the necessary technical and scientific skills to participate in not only in the construction, but also in the operation of the SKA telescope. We've got various schools initiatives to support local schools to ensure that there are qualified maths and science teachers that will ensure that school leavers are qualified to attend university and study degrees related to science, technology, engineering, and mathematics, traditional STEM careers. So there's a number of interventions that we implement locally to try to maximize or exploit the opportunities that are presented by investment in research infrastructure. And I think that's really important, is that many of these things, skills development, they don't just happen automatically. They are opportunities presented by investment in research infrastructure platforms. And you need to create programs that would exploit these opportunities. At a national level, I think there are a variety of different benefits, both direct and indirect. Direct, Meerkat itself has been South African funded, South African designed and developed. And so we've had a number of partnerships with industry to develop technologies and a number of spin-off benefits. I can mention just one, but there are a variety where we've partnered with industry to develop a passive radar system that can be used for aircraft tracking. It's different from a traditional radar system, where a traditional radar system will transmit high-powered radio signals into the sky, whereas a passive radar system just uses the natural radio frequency environment, the existing transmissions that exist from FM radio. And then we get onto the sort of indirect benefits arising from science diplomacy, recognition of South Africa as a viable destination for investment in science and technology to the international community. So, I think there's a broad range of potential benefits, and probably one of the most interesting ones that are unpredictable. But it really shows how investment in basic research infrastructure can result in direct public benefit and public good. During the COVID crisis, South Africa decided that it would implement a program to develop and manufacture ventilators. And the South African Radio Astronomy Observatory was appointed to coordinate what was called the National Ventilator Project. And in a matter of something like 8 months, we were able to source and develop a design, procure for manufacturing, get it registered, and deployed into various medical facilities around South Africa, something like 20,000 ventilators, and utilizing all of the suite of skills and competencies that existed within SARAO. They were very appropriate for a high-tech, big project development and deployment on a very short timescale. And so, what was a primarily a research institution was able to respond to national crises very quickly and very easily. And I think that's a really interesting anecdote. You can't really predict for that, but ultimately it's a benefit that does arise. But one just needs to take an opportunity and to exploit that resource or that skill or the potential benefit.
Okay, so we need to round off now. But before I let you go, let me ask a little bit about your career, because a number of young people are going to watch this recording later. You have a bouquet of degrees in fields in physics, electronics, telecommunications, computer science, and interestingly, musicology. How do all these fit into a career in astronomy?
I took a bit of a windy path. And when I started at university, I actually went to go study music, but decided I had the opportunity to merge both music as well as science. And I think what that has done, also throughout doing my PhD, I think what that did was that it always enabled me and provided me an opportunity to think outside the box. And I think having that kind of very artistic side, incubated a level of creativity within me, I think, which is really important for problem solving today, and really important to ensure that, from my perspective, when I began with the SKA project, there was a need to understand science in a system-wide level, understand how a technical change would influence a scientific outcome and would influence a financial consideration and would potentially also influence a socioeconomic impact. And having that kind of very broad system-wide view of something like astronomy and the SKA in particular, I think that creative side has certainly helped me to do that and to enable me to kind of really think outside the box. So having that sort of very broad range of skills, I think, is really important today. Just, to understand, and particularly as an astronomer, an understanding of the instrumentation that is used to collect your data is really important. Right? If you don't understand how your data was produced, how are you able to interpret it? Because the instrumentation itself has its own characteristics that it imposes onto your data. It's got its own fingerprints, effectively, that imposes onto your data. And so you really need to be able to understand that. So, I've always been someone who's like to make the links and the linkages between various things. And I guess my studies have enabled me to do that. But it's perhaps not typically a path that is traditionally undertaken by astronomers, but it's a path that I've taken, and it's a path that I've found is very useful. And typically I would encourage people who are entering into careers of science, technology, engineering, and mathematics, just take one course at university that is in the arts, for example. Just so happened that I kind of maintained all of that through to my right up to the end of my undergraduate degree. You don't necessarily have to do that, but I found it quite useful, and I'd strongly encourage it. I was honoured by my old school a number of years ago and asked to give a speech. And one of the key lessons or learnings that I communicated to the audience was, if you're going to be a scientist, learn a little bit about the arts. If you're going to be an artist, learn a little bit about science. It enables us to have a far broader perspective on life and society as we know it.
I think that's a good point for us to stop. I think there's also generally a little bit of a shift from a focus from just STEM to STEAM, with the introduction of an A, which represents the arts. Dr. Tiplady, thank you so much for your time. There's quite a lot I'd have loved to discuss with you, but we've run out of time, so we have to stop at this point. Thank you so much, and hopefully we'll have another opportunity to have another conversation.
Great, thank you very much for having me. It was a great discussion.
Thank you very much. Have a great day.